So yesterday I introduced this fourth order Q curvature, and then I have given one example which shows Q curvature on 4 manifold is the analog of Gaussian curvature on 2 surfaces. Yesterday, yes, I tried to give a geometric meaning of Q curvature. So recall what is Q curvature. So the definition is a Q curvature. I'm talking on 4 manifold on a metric G, and then there is this fourth order, what we call Penny's operator. Operating on a function is Laplace square. The leading order term is the by Laplace operator, but then there's a lower order term, and in 4 dimensions, this turns out to be the scalar curvature, and then minus this 2 times the Ricci curvature of G, and then this is differential. So flat domain, there are this scalar curvature and Ricci all vanishes, then you only see a Laplace operator. That's my fourth order Penny's operator. And then there is also this Q4. Q4, sometimes I just denote by Q in this lecture. And so without confusing, this is a fourth order in dimension 4, and denoted by Q or Q4. So in that case, this is 1/12 and minus Laplace scalar curvature, and then plus the quadratic expression, the scalar curvature square minus the Ricci curvature square. So this is all in this metric. So usually I just skip the expression, the G. And the most important relation between P4 is P4 on the metric G operating on a function W is equal, in my notation, 1/12. In some notes, this is 1/6. Then the 2 there is not there. But on the other hand, in the original notion of Bromson, there is a 2. So we have this is equal to Q4 of the new metric GW G hat, and then P4W, where my G hat is a conformal change of the metric G by E2W. And the relation, the P4 is an important operator because G hat is equal to P4 of G, and then just taking out the conformal factor. So it's a conformal covariant operator, and which prescribes the Q curvature. And today I will begin to talk about some analytic property of this Q curvature. So an analytic tool analysis. I'm sorry. No, because there are analytic now. Okay. So analytic tool turns out to be a result of Adam, which is the higher dimensional analog of Moser-Trutiger. So what the analog is saying that suppose on a domain omega containing Rn, and suppose we begin to look at the Sobolev embedding of K's derivative in Lt and function of compact support of omega. And then there is Sobolev embedding when K times P is less than N. But we are talking about And then the result says then the function W is in the ordinate class. W is in the exponential of LP prime class. For this P prime and P is a conjugate index. And actually, there is also a sharp constant. There exists a constant beta, such that this exponential of for the function has what they call the WKP norm. WKP norm is bounded by 1. So here, let me say a little bit of what this WKP norm means later. Then the integration over omega is exponential of W, and in the P prime norm, dx will be less than equal to some constant. Constant, universal constant, depending only on K on M, such that this is true, that this C, maybe this is C, is depending on beta and N, such that this is less than equal to this C times the measure of omega. This is for all W. With this KP norm less than equal to 1. And also, CNP beta is less than equal to some sharp constant. Beta is less than some sharp constant. And this sharp constant is a constant depending only on K and M. Okay, so for example, in the case when n equal to 2, and then we get back to Schrödinger Moser inequality, and this beta bar of 1, 2 is equal to 4 pi. That's the Moser-Schrödinger sharp inequality. And for n equal to 4, this beta bar of 2, k equal to 2, n equal to 4, turns out to be equal to 32 pi squared. And here, the W2P norm, 2P norm of the function turns out to be the Laplace of W, the N4 norm is Laplace W to the square norm. Okay, so in general, this KP norm has the kth derivative in LP gradient to the kth power p, but depending on k is even or odd, sometimes it means Laplace, sometimes it means, say, when k equal to 3, it's really gradient of Laplace W when k equal to 3. But we will not get into that. For our things, we want to observe when k equal to 2, the W2P form is interpreted as a function with Laplace W is in L2. Okay. Okay. So this is the inequality. Okay. So the analytic tool is this, and the version we want to use the analytic tool. The relevance to the tool curvature is as the way we derive this. When we study Gaussian curvature, we really do not use this quadratic form of, in that case, p prime equal to 2. We do not use that quadratic form of Moser-Schrödinger inequality. We use the linearized form of that. And similarly, the linearized form of this 4-dimensional Adams inequality is the following. So for this, we have that on M4, a metric G, a compact manifold. Okay. Then, if you apply this Adams inequality in this special case, we are going to have e to the 4 times W minus mean value of W on a closed manifold is d, say, v of the metric G is less than equal to some constant, so let me put log on both sides, and then that is equal to less than equal to 1 over 8 pi squared times plus W squared of dVg on the manifold plus a constant. So there exists a constant such that this W bar now is the mean value of W over the metric. So a consequence of this Argand's inequality is we have 4 times A pi squared is 32 pi squared, and that linearized form is this, and that's the form we will use. And now, the sense proof of Bosser's inequality will say now, so the question, first analytic question we are asking is, maybe we should ask that in the same conformal class, can we find some metric where this Q curvature become constant? Okay, so question, on G, this means the conformal class of G, does there exist a G hat with Q G hat equal to constant? So it's like the prescribing Gaussian curvature or the Yamabe problem in the same conformal class. Do we have this canonical measure? Okay, so in view of this Bosser's this inequality and the analog to the Gaussian curvature problem, it is natural to guess. So the theorem one should guess is theorem. If we are in an index subcritical case when the Q curvature is less than 8 pi squared, would this question have a positive answer? Okay. So the natural question is on M4 G, if the integration of QG dVg is less than 8 pi squared. This is a conformal invariant quantity, so this integration QG dVg is regardless of the representative G in the same conformal class. This constant QG dVg, sometimes I denote it by Q, is a conformal invariant. So we are saying if this conformal invariant, does that lead to QG hat is equal to constant? So that's the question. Okay. So the question is this, the analog of Bosser's program in prescribing Gaussian curvature will be something like that. Let's look at this assumption and this conclusion. So for the assumption, so in 2 dimensions, the Gaussian curvature, recall on 2 dimensions, the integration of Gaussian curvature dVg is a topological constant, 4 pi, 2 pi order characteristic. So it's always less than equal to 4 pi. And it's equal to 4 pi only when the manifold is already the sphere. This constant is equal to 2 pi only on S2, the canonical case. But if it's on M4 of G, turns out that this condition QG dVg is indeed equal to A pi squared on the canonical metric on S4. Okay. So we reach the same situation. The limiting case is A pi squared. But then there is a so the first remark is there exist many manifolds, many examples where this constant Kp is strictly less than A pi squared. So for example, example like this is involving S2 cross S2, and then S1 cross S3. These all are product metric and product metric. In this particular case, Kp, this constant, is equal to 0 on S1 cross S3. And in this case, Kp is, I don't remember the constant, but it's less than 8 pi squared. It looks like it's 6 pi squared, but I haven't computed this. And then there is also the constant, the example of the complex projective RP2 cross CP2, okay, and with the canonical metric, the Fubini metric, Fubini studio metric, and also Kp is less than 8 pi squared. And there are many examples such that this condition Q is less than this. But on the other hand, there are also many examples where this constant is bigger than 8 pi squared. Okay. There are many, this class is actually large. And for example, one example is this Taylor geometry. So for example, if M4 is a Taylor-Einstein metric, then this constant turns out to be equal to 4 pi squared and the first chain class C1 squared over 6. And from there, one can create lots of examples of Taylor-Einstein metric where the constant is bigger than 8 pi squared. I'm not going into detail because it's not relevant to my lecture today.
So you are assume the positivity of the Q culture, so.
No, I haven't assumed anything.
So
later I'm going to say something.
Yeah, so it could be negative. Is that possible?
Yeah,
okay.
There are many examples, but it's negative. It's negative. Yeah, so it could be 0 or negative. Yeah, I mean this is positive, but there are examples, but it's negative. Okay, that's fine. Okay,
for hypersurfaces in CP3, complex hypersurfaces, the probability calculation is there, no?
You can calculate
in full manner.
Yeah, complex hypersurfaces in CP3.
Yes.
Probably there is a calculation.
Yeah. There are many examples. Yeah.
And then it can get less than 8 pi square or negative.
Well, the general thing is that if it's complex hyperbolic.
Yeah. In a hyperbolic space, I should say. H4 quotient group.
Yeah.
That one can compute to see this Q is negative.
There is negative.
Yeah. In this kind of space.
No, it's possible.
In this is possible.
Yeah, it's a dual to CP2. So whether the number is large, then this number is large.
Okay. I'm sorry, I didn't. So one look at this from the formula of pi, and this is equal to y squared and plus q. So depending on the comparison of this to this, one can create q negative. The q can be negative. So the first remark I want to make is this is a real assumption. It's not like the two-dimensional case. Everything is less than 4 pi, unless you are already on S2. And now, it turns out that this question is not true. Okay? So even if we are in a subcritical case, we still do not, in a conformal class, achieve the imp. And the question, the additional assumption we have added is, let me call this as a result by myself and Paul Yang. So what we have added is we observe that if additional assumption is, if we assume this is positive, this operator P is positive, and the kernel of P consists of constant. It always Q constant, but suppose the kernel of this operator consists only of constant, then there exists some G hat with QG hat is equal to constant. And we are actually, we say a little bit more. Okay, let me say that. So in fact, what we have proved is the corresponding functional for prescribing Q curvature attains in. Actually, in this case, once we begin to consider this functional, for some reason I call it 2 of W. And that functional is the analog of the Moser functional for the Gaussian curvature equation. So that functional is, as you expect it is equal to P4W, W, and dVg, the energy functional, and plus 4 times Qg and W dVg. And then we normalize it such that this integration Qg dVg, and then there's a volume normalization log of integration P4W dVg and dVg. A volume normalization. Actually, in this case, so this is a continuation of the statement of this theorem. In the case of in theorem 1, actually says 2 of W in of this in the class is achieved under the assumption. Okay. So we put, since we are trying to say something in the conformal class is true, this condition is a condition of some conformally invariant quantity, and the sign of the operator is also a conformally invariant condition. So under this assumption, we attain the imp of 2. Okay. So, and this is, the proof is almost the same. Here I did write down, it's S2 plus S3. This is equal to 16 pi squared over 3. And for CP2 is 6 pi squared. So and there's just computation. And so I want to say that this imp is achieved. Okay. So so here is a sketch of idea. I want to say that why this P4W, PGW is positive is important for the imp to be achieved. Okay. So there's additional assumption. So we look at this and we follow the same strategy of proof like this 2-dimensional case, and we apply this corollary. And we see what we have. So in this case, this P4W, the inner product is, we write it down, is equal to Laplace W squared. So let me just skip the G. And then plus 2/3, and then the scalar curvature and gradient W squared, and minus 2 of the Ricci curvature. This is a tensor, so I operate in it. I think about this as an IJ component and WI WJ. So I write down this in terms of the definition. So apply this corollary. Of this Adams corollary, and then what we really have is these 2 of W. We plug in this P4WW into this expression, and then we have Laplace W is greater than that thing. Okay? And the first thing I should say that I have write this constant in the way 2 times W. This is a functional which is invariant under shift. So W and plus C and W is the same. Okay. So plus any constant C. So constant C. So for that reason, in that inequality already, although there's a mean value of W there, you can think about the mean value as 0. You shift this, the functional is the same. So 2 of W, if you use that, this would be greater than equal to 1 minus integration QG dVG, and then A pi squared, and then there's a Laplace W squared, and then plus the rest, plus this thing. 2/3 R gradient W squared, and minus 2 VC, and WI WT, and plus a constant. I mean, a lower order term, but let me think about this as a lower order term. So one apply corollary, we get this. So if the assumption is integration QG dVG less than A pi squared, and what this says is, in this case, we think about this scalar curvature. We are fixing a manifold, so this integration of QG dVG less than A pi squared would imply that for the minimum sequence W, say L, this minimum sequence would have the gradient W term bounded by Laplace W term. So this is a positive constant. Okay. So it would imply that gradient of WL square is bounded by some positive constant. This constant is, say, A times Laplace WL square. Okay. And plus some lower order term under the normalization. So this seems to say that, I'm sorry, the other way around. Okay, so in for this. Okay, so that means this thing is bounded by that thing. Okay. So the higher order derivative of the sequence is bounded by the lower derivative of the sequence. That seems to strongly suggest that its function should begin to converge in W1 norm, meaning in a suitable norm. Okay. But it turns out this is not the case. Okay. So it turns out that what happens is, for some example, this happens for the minimum sequence, both tends to infinity. This minimum sequence has the effect that W22 norm and then W12 both tends to infinity. Okay. And what is such an example? It turns out that, so the remark here is, we worry that WL has this first derivative norm and the second derivative norm both tends to infinity. So there's no control. Okay. And to see this is really happening is, we look at the condition PG positive. Okay. So suppose PG is positive, it turns out this is essential for this situation for WL, for such WL not to exist. So let's look at the example. One example is an example of M. So example is, we look at this hyperbolic space, genus 2 hyperbolic space. Sigma 2 cross sigma 2 hyperbolic space, genus 2 hyperbolic surface. And in this case, the first, and choose some hyperbolic surface, this is my sigma 2. Sigma 2 is, say, very small. I take the 2 surface cross 2 surface, and this is very small. So in that case, we look at this P4. Remember, P4 in an Einstein space is just conformal Laplace composite with Laplace. So in this case, one can justify this to see this is just Laplace squared plus Laplace. adjust this constant so that this is 1. So adjust this scalar curvature. So in this case, and this fact would imply that there is some function Laplace phi which is equal to lambda 0 phi for lambda 0, which is very small, and lambda 0 positive on these two surfaces. And then we look at a cross surface. And so P4 of phi in this case will be equal to lambda 0 squared minus lambda 0 times phi. In this example, and so this is, let me denote that by lambda phi, and where lambda is negative. So in this case, this operator P4, although the leading order term is Laplace squared, it has a negative eigenvalue. And if once it has a negative eigenvalue, one can begin to compute this 2 of xi times phi, a multiple constant xi times this eigenfunction, and one compute to see this is lambda xi squared and phi squared and plus 4c times q phi, and then minus integration q of integration, there's a log of e to the 4c phi. I just substituting w by c phi. And turns out one compare the order of this term to that term. Okay, and here is exponential 4c phi. So it's like e plus e 4c phi. So the point I want to make is here we have c squared and there we have c. So this is the term which is a dominating term. As c tends to infinity. Okay, as c is very large, it becomes this. So this whole thing tends to minus infinity as c tends to infinity. That's the point I want to make. Okay. So when P4 has a negative eigenvalue, we do not expect this functional 2 to be bounded from below. Okay. And what happens is this minimum surface, minimum sequence, both, although the lower order term is bounded by the higher order term, everything goes to infinity. And now let me say that if P4 is positive, why situation is better? And it turns out that in this case, one can improve the Moser-Schrödinger inequality. So the lemma is if P4 is a positive operator, this P4G is positive operator. And then one can improve the Moser inequality. In this case, we have 32 pi squared, and then we have W minus mean value of W squared. And it used to be, we divide the whole thing by Laplace W squared. We know that is bounded. That's the Adams inequality. And it turns out that in this case, we can replace the W22 norm by this P4 W norm. Improve it a little bit and squeeze in some lower order terms in the case where P4 is positive. Okay. So if this P4, P is my PG, it's a positive, then this is bounded. So bounded. So assuming this lemma, then assume the lemma. Assume the lemma. Then let's look at this 2W. So in that case, this 2 of W, I do not really bound this P4W using this Laplace W. I treat this as a whole. And now, here, I can can think about this as W minus mean value of W, because one can shift constant, and here is W minus mean value of W. The way I look at it is I squeeze in the constant W minus mean value of W. And then I apply this inequality or a corollary of that inequality instead. And the constant I get is this is A pi squared. And now I P4 W and plus 4 times Q times the mean value of W, and then plus the constant. This constant is a log of that constant xi bar or something. So I get this inequality. Okay? And now it's a greater than equal to. So I have this inequality. So what I can do now is I assume that the kernel of P only consists of constant. So its first eigenfunction is positive. Okay? So this is greater than equal to lambda 1 of P. So lambda 1 of this P4, the operator times W2 naught. That's squared. L2 naught squared. So then in this case, you will see that this W2 naught squared is bounded by the W2 naught. So that would imply for the minimizing sequence WL, the WL2 naught is bounded. Since in quadratic is bounded by since in linear. And once one gets the lowest order term WL is bounded, one can return to the original proof to see it begin to jet up. Okay? So this implies that the plus WL2 norm is bounded. And so on. Okay. And that finishes the proof. So that's the original theorem. We pointed out that adding some additional assumption, then the inf of the functional is bounded from below. Okay. And now then the natural question is, when is this holding? When is this operator being positive? When does that happen? And we didn't really address that problem, and it turns out that later on there is a remarkable result of Gursky, which says there's a natural condition such that it's holds. So this is a result of Gursky. So Gursky's result is to say that on M4G, the first observation is if the Yamabe constant of M4G is positive. So the Yamabe constant is equal to the inf of the scalar curvature in a same conformal class of G divided by the volume of G and to the suitable scale power, so that should be equal to n minus 2 over n. Okay. And this is a conformal invariant because you involve all metric in this class, so it's a natural conformal invariant. So for example, if scalar curvature of the original metric, this representative is positive, then the Yamabe constant is positive. So, but we like to impose condition such that this is a conformal invariant constant. And Gursky's observation is a simple one, but it's going to be useful. Then he said that this constant, this invariant, is already less than equal to A pi squared. Yeah. And equal to A pi squared only on the canonical case. That's an observation. And then he also proved the other result is if this constant is positive, this invariant constant is positive, and if this fourth order invariant invariant is also positive, then, so there are these conformal invariant conditions, which is a natural condition, imply this fourth order operator PG is positive. Okay, so combining theorem 1 and theorem 2, we do get the very nice result to say that on M4G, if the Yamabe constant of Mg is positive, and then this invariant constant is positive, imply 2 in or 2 is a 10. So in this slice of manifold where we have this control, then the in is a 10. Combine these two to get this. Okay. So now let me say how to see Gursky theorem. So before I say so, let me say that in Gursky theorem is a non-trivial. The step 2, it turns out statement 1 is easy, but the statement 2 is highly non-trivial. And the statement 2 here, one look at it, the thing is this P4 is an invariant operator, conformal invariant operator. So its positivity should be a consequence of some conformally invariant condition. Okay. And this is the condition we talk about. You are not going to impose pointwise condition of scalar and Ricci to make this positive, because the pointwise condition of scalar curvature or Ricci will not be a conformal invariant condition. Okay. So the reason why this is a nice result is the condition are natural. So now let me say a little bit about the proof of Gursky's result. Before I begin to sketch the proof of the result, let me say that it turns out there is a theorem 3. Gursky's result is actually around 2000. And the proof of this, I have in my lecture notes, Zurich lecture notes, I have organized this proof in page 46 to page 50. And for this result in 2006 was improved by Gursky and Liakovsky. In around 2006. So what I say is actually if Yamabe constant of M4G is positive, and it turns out that you only need this constant Kp. Kp is equal to plus 1/6 of Yamabe constant is positive. In this class, you squeeze in 1/6 Yamabe squared. If that is constant, is positive, then this implies this P is positive. Operator is positive. Okay. One squeeze out a little bit more. So, and the reason one can squeeze out a little bit more is a little bit contained in the original proof of Gursky. But the sharp constant really depends on some later development of the subject. I will not sketch the proof of here, but let me say that the thing which is going on here is it turns out this Q curvature is a fourth order curvature invariant because of the Laplace term. Differentiate a metric twice and then 4 times. But we already noticed that on full manifold, this integration of Laplace R is always equal to 0 for closed manifold. So one wonder why it should be there, why it is natural there. It turns out that the important thing is to observe the quadratic curvature term. And the quadratic curvature term turns out to have, so here is a little bit of a brief history or some outline. So this is just a remark. Not some remark, but let me say that this quadratic curvature term has a geometrical meaning. Turns out has geometrical content. It is difficult to estimate this term because there's a minus sign there. So there's some cancellation happen. It's not something square. So there's a polynomial subtract another term. And the geometrical content is really developed, observed by Bialkowski in his thesis. And in his thesis in year 2000, a little bit after 2002 or something. And here, what he did is he began to study the curvature tensor, Rm. So this is the full Rijkl, the full curvature tensor. And then he said that from the Cardin's point of view, there's a decomposition. And the decomposition is this tensor, Ijkl, is file direct sum with something called Shelton tensor and weight product with Shelton tensor. So what is this Shelton tensor? So this AG is called Shelton tensor. And this Shelton tensor is 1 over n minus 2 times Ricci curvature minus scalar curvature divided by 2 to the n minus 1, the curvature. This is a 2 tensor, which is this tensor, a strange combination of Ricci to scalar. Okay. So the 4 remaining tensor has a natural decomposition into the Weyl part and the Shelton curvature part. And then this, so that in conformal geometry, we already know this Weyl tensor changes pointwisely. This is a pointwise conformal invariant. By putting out the conformal factor. So this part, the Weyl part, when you change in G to G hat, the behavior is fixed. Nothing to do with derivative of W or something. So it's just a fixed part. So that means if you are going to study the geometry, you are going to study how does the remaining tensor G changes under conformal change of metric. All the behavior of change is reflected in the change of the Shelton tensor. So that means one should study the Shelton tensor under conformal change. We are interested how Shelton tensor changes under conformal change. And now, so we have this, in some sense, n cross n tensor. One thing to think about is the matrix. Okay. And if we are going to study the behavior of such a tensor, one should study its eigenvalue. Okay. And it turns out the trace of this Shelton tensor is just a multiple times the scalar curvature. Actually, it's equal to 2 to the n minus 1 scalar curvature. Trace of this metric. And that's because the trace of Ricci is scalar. So one does some computation, one sees that. So that means that the study of the scalar curvature under conformal change, that's the Yamabe problem, is the study of the trace of this Shelton tensor. And if we are going to do with the higher analog case, one should begin to study called the other eigenvalue, and in particular, what's called the symmetric, elementary symmetric function of the tensor of a metric n. So this is the case elementary symmetric function of the eigenvalue of the tensor A. Or think about A as A plus this. So what is sigma 2 of A? Sigma 2 of A is sum of lambda I, lambda j. Okay. Sum of lambda I, lambda j, and I less than j. So by definition, it's equal to this. So look at this lambda I are the eigenvector of A, and then one study this. And so one should think about this when sigma 2 of A, one should think about it as the norm of A square minus the trace of, so one think about lambda I, lambda j as lambda I square and minus sum of lambda I square, things like that. So it's 1/12 the norm of A square and minus trace of A, sorry. I want this other way. So it's trace of A square minus the norm of A square. So sigma 2 of A is equal to this guy. And since in this case, if A is the shortened tensor, if A is our metric shortened tensor of A, so this is true, this is definition true for any n cross n matrix. And suppose we take A to be this shortened tensor, then in this case, the trace of A is already the scalar curvature, and then the norm of A is the Ricci square. Okay? So in this case, this is equal to some constant, which I will not write down. So this is equal to, turns out to be equal to R square AN minus BN of the Ricci norm square. So one do the computation of trace A, one get this. And it turns out that when n equal to 4, the sigma 2 of the shortened tensor is just a combination. The ratio between these two constants is R squared minus 3 times Ricci squared. Multiple. I can never remember this multiple. Maybe it's 1/12 or some constant of this. So the ratio is the same as the ratio in our Q curvature. Okay. So Q, in this case, is equal to minus 1/12 Laplace R plus a constant times sigma 2 of the shortened tensor. So that's the remark. And why is this relevant to us? Okay. The relevancy to us is that one begins to realize that there is another geometrical meaning of this quadratic part of the Ricci curvature and modulo the Laplace R part. So I will come back to this point later. And now, with that remark, I will begin to prove the Gutsky theorem. So come back to the proof of Gutsky result. The proof. So, okay, I'm sorry, I'm a little bit jumping around. Okay. The point I want to make of theorem 3, one uses fully the aspect that there is this structure of the quadratic part of the symmetric function of a Shelton tensor. So the study of this, and if AG, G hat, if one look at AG hat, it turns out that is equal to the hashing W plus a constant times a part of gradient W squared, and then minus I'm not 100% about this WIWG. So AG hat is a Shelton tensor whose quadratic part is this thing, and then plus GIJ and plus, so it's just this. So under conformal change, one sees this. So the study of the symmetric function of sigma 2 is like the study of the symmetric function of the Shelton of this hashing of W. So that's a study of the falling linear PDE.
You can add background linearity here.
So there is a constant here, it's all right, depending on your sure, plus AG. Okay, sorry. Yeah. AG here is AG. Yeah, so there is a shift of constant. Okay. So in that case, so the only remark I want to say is in the proof of theorem 3 uses techniques in the study of the sigma 2 of the Shelton tensor, of falling linear PDE, that results in falling linear PDE, and which was later developed before the subject was developed. This fact was observed later. Okay, so the proof of theorem 3 involved techniques which are much deeper. Now, let me say that proof of Guski's original theorem. Okay. And here, the part 1, the first part is to say that if the Yamabe constant is positive, then the scalar the Q curvature is already less than equal to this. So in this case, we already observed that the Laplace part is not important. So this is the same as the dVg. And there's a constant. The constant, I'm sorry, 1 short or 1 over 24. There is a multiple of the constant here. So this is sigma 2 of Ag dVg. And so if our assertion is if the Yamabe constant is positive, would imply sigma 2 of Ag dVg, this quadratic part has a bump. Okay? Now how to see that? So in that case, this is the scalar curvature minus 3 of Vc squared. And in all this type of analysis, one compare with model case. So that means instead of writing things in terms of Vc curvature, one should think about when does the Vc curvature is in the Einstein case. So in this case, in 4 manifold, the Vc tensor is its traceless part plus 1/4 the scalar curvature. Okay. And for Einstein metric, the Vc traceless part vanishes. Okay. So that means one should rewrite this Vc curvature square in terms of the traceless Vc square, and then one compute to see this is actually 1/4 of R squared. Okay. And one substituting this in, and one get this is equal to R squared minus 3/4 this. So this is equal to 1/4 of the scalar curvature square, and minus 3 times the trace species squared. Okay. And at this point, one use the key fact that notes that this constant up to a constant, this is a conformal invariant. So that means to compute the size of this constant, one can choose any metric in its representative. Okay? So you compute this, you can choose any g hat to compute. So that shows that in this case, maybe the good representative is the Yamabe metric. So we choose G to be equal to G Yamabe. Okay. So the famous problem of Yamabe is to say, in this case, the scalar curvature is positive. Okay. And so that means that this is the constant. And our assumption this y is positive means this constant is positive, and it's the minimum of the Yamabe metric. Okay. It's the minimum of y, the function of y. So if one does that, that shows this is less than equal to 1/4 of this gy squared. And after that, we are in good shape because this gy squared is a constant. So we take it out, and this is equal to 1/4 of gy squared times the volume of this gy. And in full manifold, one sees the ratio of this thing, and this is exactly equal to 1/4 of the Yamabe constant yg squared. A definition of the Yamabe constant. And now we begin to use the famous result in the development, which says that the Yamabe constant is always less than equal to that of the fourth sphere, and it's a 10 only on fourth sphere. Okay, so recall that. So this is less than equal to 1/4 y of Yamabe constant gc squared, and a 10 only on S4 gc. Okay, so this is a simple observation, but that used crucially, we are computing something which is Yamabe invariant, which is a conformal invariant. So that finishes the part of 1. Okay? And this constant is exactly what cook up on the fourth sphere, the Q curvature is a pi squared. And so this computation shows this constant is less than a pi squared, a 10 only on fourth sphere. And now, so I have finished the proof of this part. And now, why does this constant positive imply the operator is positive? Okay. So how do we compute the eigenvalue of P4 using these two constants? And this turns out to be a fact which is implicit and has something to do, again, the insight from the two-dimensional Gaussian curvature equation. So here is some background. It turns out that on two surfaces, I have this functional J, which is the functional to study the Gaussian curvature. Recall J of W. This is the functional whose Euler-Lagrange equation is the prescribing Gaussian curvature property. But it turns out that this is the functional to study Gaussian curvature equation. Okay. But this functional turns out to have another geometrical meaning. Okay. So this functional turns out to be the same. I have skipped a little bit of detail. Okay. this is under the normalization. The volume of the metric is the same as dBg is the same as dBg. Under the normalization is also the log determinant functional of the Laplace operator. And this computation is done by Polyakov. That's called Polyakov formula. So if I will not go into detail saying how to define the determinant of the Laplace operator, but the quotient of that is this functional J of W. So with this in background, in conformal geometry, in four manifold, one tries to extend this Polyakov formula in four manifold. Okay. So this means that there are work by okay. So Bronson, Yuki, and also this Danish mathematician.
Orsted.
And so on. So let me skip detail. And so one begin to study on four manifold G, one begin to study log determinant of the conformal Laplace operator GW divided by determinant of L. Okay. And this formula, so one would like to study this functional f of W equal to this. And the formula is complicated, but on the other hand, it turns out that one can analyze it and give it geometrical meaning. And the Euler-Lagrange equation of f of W, f prime of W equal to 0. So one studies the extremal metric of the log determinant formula. One studied this. Okay. And it turns out this formula is equal to QG, the extremal function satisfies this QG hat plus something called Laplace R of G, and sometimes I use gamma 3, and plus something gamma 1 of Weyl square of G equal to constant. So some constant, for some reason I use it gamma 3. So there's this Q formula, and then there's Laplace R formula and Weyl R. So the extremum functional of that. And the Laplace, in 4 dimensions, there is a coincidence. So one fact is, if one look at what is Laplace R, the functional of that is 3 of W. This is conformal of G hat square minus RG square. And the conformal Laplace 3 point square equal to 0 is correspond to minus Laplace R equal to constant. So the Euler-Lagrange equation of this part, Laplace R, comes from the study of the quadratic difference of this. Okay. So the offshot is, that shows that to study the Q curvature problem, the nice representative of that may not be the Yamabe metric, but a metric which corresponding to extremum of log determinant function. Okay? And that's the fact which Gursky employed in his proof. He says that in certain sense, if we want to prove this P4 is positive, the good representative should have something to do, not only the functional 2, but some multiple of functional 3 comes from functional 3. So I will not have time to go into detail, but let me now outline the proof of part 2. So there are steps. Okay. So the first step is to notice that step 1 is to say that we can really solve Q minus gamma 3. For some reason, I used minus gamma in the original notation. So a Laplace R equal to constant is solvable for gamma 3 equal to 1/6. If one add a little bit room of this, then this equation is solvable. Okay. And remember that for Q to be solvable, for the critical point to exist, we need some condition. But add this auxiliary functional, we don't need a condition. And that is solvable at certain range. And that has something to do with extremum exists. Okay. And now, okay, so in this case, if one chooses this good range, this is the same as Laplace R equal to lambda plus 2 of sigma 2. And where lambda equal to minus 2q curvature, because the integration of this is equal to 0, and the lambda integration with sigma 2 is just the same as q. And the assumption integration q is positive means this is negative. So that's the only equation we are going to use. And now that is step 2. The step 2 is now the Yamabe constant is positive. Under the assumption Yamabe constant is positive. And Laplace R equal to lambda plus 2 sigma 2. And with lambda negative. One can show in this case, this would imply a conformal Laplace operating on R. Remember, this is equal to minus R plus 1/6 R squared. And if one plug in this into this expression, one can see this thing has a sign. Lg of R is positive by plugging this in, and this 1/6 R squared cancels with this guy, and you have some traceless VC squared minus lambda. And okay. So the conformal Laplace on R is positive. So here is another lemma of Gursky, which turns out to be very useful later, which says if Yamabe constant is positive and the scalar curvature, conformal Laplace operating on R is positive, you can now compare the scalar curvature to if y of g is positive, this implies Lg is a positive operator. So LGR is positive, and this operator has only positive eigenvalue. So R can be compared to be the first eigenfunction of conformal Laplace. There is a maximum principle. So this maximum principle compared with first eigenfunction of R would imply R is positive. So you are achieving a metric which satisfies this condition and the scalar curvature is pointwise positive. So that's the second step. Now, with that, one can begin to compute the step 3, one can begin to compute P4WW. Okay. And now this is equal to, let me use phi, not to confuse it. This is for any function phi, we are going to show this is a positive function. So this is equal to the cos phi squared plus 1/6 r times gradient phi squared. This r is positive, so we have two positive terms, and then there is the traceless Ricci term, 0 times gradient phi, gradient phi. So we wonder, how do you deal with this term? Thing. Okay. And it turns out we can deal with this term using first the standard Buckner formula. Which deal with the hashing of phi squared to Laplace phi squared and Ricci squared. So in this case, I have hashing phi squared is equal to Laplace phi squared and minus Ricci gradient phi on a compact manifold. So that's the Buckner formula. And then the other thing one uses, even at this stage, it's not a direct estimate, this term cancels. One uses the fact that the other fact one uses is if E is a traceless Ricci tensor, metric, N plus N metric. So if it's trace-free, the trace of E is positive, then E operating on a vector x, the norm square will be, so if you look at Eij, xi, xj, the summation of that will be less than equal to the norm of E squared. That's the Hilbert-Schmidt norm, and the constant here is improved. That constant is n minus 1 over n. Okay. So in 4 dimension, we improve a little bit constant 3 over 4. Okay. So with that gain, one can plug in these two facts and showing this thing is these two facts add up to prove this is positive. Okay. It's positive. So that's the proof of Guski's original theorem. And later on, of course, there are other ways of showing it, but this proof is nice that it explored other geometrical facts of this Q to the extremometric of the log determinant function. Okay. I think I should end my talk today, but what I will do tomorrow is I'm going to discuss the positivity of Penny's operator in general. In particular, I want to talk about the positivity of P2 gamma operator, where gamma is a fractional number. So suppose I have P2 gamma, which is minus Laplace to the gamma power and so on. And it turns out on certain class of manifold, there is a conformal covariant operator, which is the leading order term is minus Laplace to the gamma power and has conformal covariant property. And I want to put it in a prospect how to show this operator is a positive operator. It's a non-local operator. On the Euclidean case, it's minus Laplace to the gamma, so it's always positive. But on general manifold, when is this positive? And for this, we use the recent result of Caparelli and Silvestro on this computation of non-local operators. So that's what I plan to cover a little bit tomorrow. Thank you.